Okay, for example number 4, we're on 3.6 part 2, and we just have example 4 and example 5 now to go. So find a tight upper bound for the approximation to the integral of cosine x over x dx from 1.87 to pi. Using the midpoint rule with n equal 43, note that the second derivative of cosine of x over x is a decreasing function on the bound from a to b. Okay, so let's look at our equation. Our equation for midpoint is m sub n is less than or equal to capital M. Now some other places, other books, use a capital K to represent your derivative there. So this is going to be our second derivative. The biggest value of our second derivative, b minus a cubed, Casey, over 24n squared. All right, and so we're just going to go through and plug in all of our values. Now on some of these, when you need to find a derivative that's not super easy to find, just go ahead and use a derivative calculator online or something. I did go ahead and do that on this one when I found my second derivative. So find your second derivative and plug in 1.87. Okay, so the whole reason they tell us this information right here, that our second derivative of this is decreasing. So that means on the bound from 1.87, that derivative is decreasing from there. So that tells us that the largest value is going to be on the left-hand limit. So we're going to plug in 1.87. If it would have said it's increasing on this interval, I would have used the last number. So since this one is decreasing, I'm going to find my second derivative, and I'm going to plug in 1.87. I did use a calculator to do this, and the answer that I got was 0.613999. You use lots of decimals on this one, on all of these error ones. Okay, so we're going to use that for our m value. So that's equal to m. B and A are right here. Those are our bounds. And then n is going to equal 43. So that gives us enough information to find all of this. So m sub n is less than or equal to 0.613999 pi minus 1.87 cubed all over 24 times 43 squared. Plug that all into your calculator. Make sure you use lots of parentheses. Get everything in the denominator in parentheses. Make sure you're using your cube right. So be careful how you put that into your calculator. And then you should get a final answer of, must be on my calculator. Okay, let me find that answer. Okay, so I got it. It's right here under my nose. So m of 43 when n is 43. Our error, maximum error, is going to be 0.0002844888. Okay, and then that is the answer that we need for example number 4. Okay, so our last example for 9.2, wrong class, sorry, 3.6 part 2. Example number 5, how large should n be to guarantee that the trapezoidal rule to the integral from 2 to 4 of that equation is accurate to within 0.001. So we need to use our equation for the error bound of the trapezoidal rule. So we have t sub n is less than or equal to capital M, which for trapezoidal rule is going to be the largest value of the second derivative of f, and times b minus a cubed all over 12n squared. Okay, so that's the error-bound formula for our trapezoid rule. So we need to know what the highest value of the second derivative of this function is. So if f of x is equal to negative x to the fourth plus 12x cubed minus 48x squared plus 4x minus 1, then f prime of x is negative 4x cubed plus 24x, no, that's a 3, isn't it? 36x minus 96, 36x squared, 96x plus 4. There we go. Second derivative is going to be negative 12x squared plus 72x minus 96. And if you're to graph this, you'll see that it is a parabola that opens down, that goes through the points 2 and 4, and that right in the middle of those two is the vertex at 3. So we want to know what f double prime of 3 is equal to. That's going to be its maximum value. You can use Desmos on this, that's fine with me, to find your maximum value there. Not too hard to find though, it does end up being 12. So for your second derivative, highest value is 12. So we're going to put that in for n. In the problem here, it tells us, oh, we want to know what n is. That's right, we're solving for n on this one. So we have 12, and then b minus a, which is 4 minus 2, cubed, over 12 n squared. Now, we want our error to be accurate within 0.001. So I'm going to put that here on the left-hand side, 0.001. Now I have an equation that I can solve for. These 12s will cancel. I can multiply n squared to both sides. So I get 0.001. 4 minus 2 is 2. 2 cubed is 8. So let's bring n squared over there too. I think I said that. And then we get 8 on the right-hand side. So we're going to have n squared is equal to 8 divided by 0.001, and then take the square root of both sides, and then we will have n. So on that one, I had n is equal to 89. There we go. 89.4427. Oh, my pen is really not working now. So we can't have a partial subinterval, and we can't round down. So that tells me that I'm going to have n equal to 90. So if I have 90 subintervals on this equation using the trapezoidal rule, then I will be within an error of 0.001. Okay, now we got just another half of this, and then we'll be done. Okay, for the second part, now we're using the same exact equation. Everything's the same except for now we're using the Simpson's rule. So we want our error, again, to be within 0.001. Let's write down our equation. So we have S sub n is less than or equal to m times b minus a to the fifth over 180 n to the fourth. And this is where m is the absolute value of the fourth, the absolute value of the highest value of the fourth derivative of our function. So our second derivative, let's go back to where we ended off in the last one. We ended off with our second derivative being negative 12x squared plus 72x minus 96. Now we need to go to our fourth derivative. So our third derivative is going to be equal to negative 24x plus 72. And then our fourth derivative is equal to negative 24. So we want the absolute value of that to go in for m. We want s of n to be accurate to 0.001, so let's set it equal to that. Negative 24 was our n, our m. b minus a is 2 again, so we're going to have 2 to the 5th power. Oh, and we can use absolute value, so we don't have to use the negative. So positive 24, 2 to the 5th, 180 times n to the 4th. Okay, I'm going to multiply that into the 4th to the left-hand side. So we have 0.001 into the 4th. And then on the right-hand side, we have 384 over 180. Then we can determine what that is. Divide both sides by 0.004 or 0.001. Take the 4th root of both sides, and we end up with n equals 8.08. Now, one thing I don't think I've mentioned with the Simpsons rule. Remember how when we did the Simpsons rule, we are taking two partitions. So let's say we had x sub 0 here for our first endpoint, and then x sub 1 and x sub 2. Well, with the Simpsons rule, it took 2 intervals for us to be able to write our quadratic equation. So what that tells us is for our Simpsons rule, we always need to have an even number of intervals for Simpsons rule. Now, we haven't ran into that problem up until now, so we need more, just a little bit more than 8 subintervals. So we have to round up, but we can't round to 9 because that's an odd number. So we need to round up to 10. So final answer for this one is going to be 10. If we have 10 subintervals, then we will be accurate to within 0.001. And that's all we have for 3.6.